Welcome everyone. This is the second video of sampling distributions. Remember, in the first part we talked about X bar, and when we're talking about the sample mean, there are two possible sampling distributions: the normal distribution and t-student. Now in this video we're gonna mention the sample variance. So when we're trying to analyze the sample variance S squared to make an inference about sigma squared, there's only one possibility, and that will be the chi-square probability distribution, which again is a sampling distribution. Okay, so there is only one case for the sample variance. So if the original variable x comes from a normal population, then the way in which we standardize in the chi-square probability distribution, it's by measuring the chi-square equal to n minus 1 times the sample variance over the population variance. So once we want to find probabilities in the table or the value of a critical chi-square, we will need the degrees of freedom n minus 1 that will be required in the table. Degrees of freedom and probability will give us the chi-square value, or with the degrees of freedom and the chi-square value we may get the probability depending on the situation. So let's check an example when we're going to use this probability distribution, the chi-square. A company that manufactures electronic chips claims that the products have standard deviation of 40 hours. That will be, since it's a claim of the company, then that's a parameter. That value wasn't measured using a sample. Find the probability that in a sample of 16 chips, the standard deviation is greater than 42. So here the notation matters. So the problem is asking about finding the probability, and here the random variable in the problem is the sample standard deviation. S is going to be greater than 42. That's the probability here. The probability that S is greater than 42. So if you want to find the probability, then you need to standardize. But you cannot standardize to a normal distribution because Z is not a sampling distribution for the standard deviation or the variance. So what we need here is the chi-square. So instead of Z, we will find chi-square, which is a different probability distribution, of course. So let's use this equation, n minus 1 times the sample variance, that's 42 squared, over the population variance. That will be 40 squared. So the chi-square value here is 16.53. This means that if you want to get the probability that the sample variance is greater than 42, this is equivalent, and this is why we find these values, right? This is equivalent to the probability that the chi-square is greater than 16.52. So this is the reason, guys, why we're finding this statistic value, the chi-square value, because we need it in order to compute the probability. So it's the same thing as we did with the X bar, but in the case of the X bar, the sample, we were using the normal distribution and t-student. But when we're talking about the sample variance of a single population, we use chi-square, which is a different probability distribution. Alright, so if you go to the tables, then you need to find the probability for a chi-square that has 15 degrees of freedom. Remember that the n is equal to 16. Degrees of freedom, it's n minus 1. That's how we get the 15. If you go to the table, degrees of freedom 15, and you have this value of 16.52 from inside the table, then you will get the probability to the right, because this is the area to the right. Be careful, you gotta check if your table goes to the right or to the left, or if you're using Excel, you gotta make sure that you're getting the right tail, like going to the right in this case, because it's greater. So if you do that, you will get that the probability is 0.35. So what is the interpretation of this? It means that if we draw a sample of 16 units of chips and we analyze the sample standard deviation, and we want to measure the probability that the sample standard deviation is greater than 42, given that the population standard deviation is 40, so that probability is 0.35. So if this is true, I mean if the process has a standard deviation of 40, then the probability that a sample is going to be greater than 42 is 0.35. That's the meaning of this probability. So if you want to draw it, the chi-square is not a symmetric probability distribution. It's not symmetric. And it doesn't have negative values. So if you find the 16.52, then we're getting the area to the right, which is equal to 0.35. That was the question in the problem, to get the probability that S is greater than 52. That's equivalent to the probability that the chi-square is greater than 16.52, and now we're getting that probability here. So this is why we call this chapter as sampling distributions, because we're analyzing statistics that are measured using a sample, and we need a probability distribution that will model those sample statistics. So that will be the normal, t-student, chi-square, as in this problem, and later on we will see that there is one more, which is the Fisher probability distribution. Alright, so an additional case here, it's when we're talking about proportion sampling. So if P, it's the proportion of success in a binomial distribution, remember that P hat is the sample proportion. Then if we check the following, that NP and NQ, both of them are greater equal than 5. So if that happens, then we can approximate to a normal distribution. We can approximate to a normal distribution. So here the real population is binomial. But if we can check these two conditions, then we can approximate to the normal distribution. So we can use Z to estimate probabilities. So let's see a quick sample of that. It says in the production of metallic doors, it has been estimated that 5% of the daily production is defective. So please note that this 5% is given as something that is a part of the process. It's not like based on a sample. That means that that's P. That's a value, that's a guideline of the process that is known. Alright, in a sample of 100 doors, answer the following question. Estimate the probability that the proportion of defective doors in the sample is greater than 6%. Greater than 6%. So the question here is about the sample proportion P hat. So what's the probability that P hat is going to be greater than 0.06? The assumption here is that the true parameter, the true proportion is 5%. It's 5%, right? 0.05. So you want to check like what's the probability that if you draw a sample of 100 products, what's the probability that that sample will have a proportion greater than 6%. So we want to get this probability, then we need to make an approximation, right? So let's first check if it's possible. So NP and NQ. So if you do NP, that will be 100 times 0.05. So this is 5. Remember, it's greater or equal, so it satisfies this condition. And of course, if we have 100 times 0.85, that's Q. This will be greater than 5, right? Greater than 5. This is 95. Then both conditions are satisfied, so we can approximate, or we can get this probability by a standardization. So let's do that. I'm going to use this equation. So P hat minus P over square root of PQ over N. Therefore z it's equal to p hat 0.06 minus 0.05 over pq 0.05 times 0.85. This is over 100. Then we get that the z value it's 0.458, right? So what is the interpretation of this? What is the interpretation of that z? So this z is, okay, if you want to get the probability that p hat is greater than 0.06, then this is equivalent to finding the probability that z is greater than 0.458. So once you get this probability, you're finding the original probability. Let's get that probability. So let's find a normal distribution table. So we can check the value. Remember the z is 0.458. So I'm gonna get a table. Remember that there are some tables that go to the left, other tables go to the right. So it doesn't matter which one you're finding as long as you are consistent. So far most of them that I have seen here are to the left. I'm gonna use one to the left. That's fine. I'm gonna try this one. Let's see if it's complete. It has only negative values, and my value it's positive. I can use it, but maybe I will confuse you a little bit. So let me try to check if there is another one. Okay, let's use this one. So this area goes to the left, be careful. Then the z value that I'm finding it's 0.458. So it's 0.4. So here I'm getting the 0.4. And the 58, I'm going to round it up to 6. So 0.46. So we find the intersection of 0.4 and the 0.06. This will be 0.6772. But that area goes to the left. And remember that the problem is asking greater. It's asking the area to the right. So I'll do 1 minus 0.67. Then this probability is 1 minus 0.6772, right? And that's how we get the desired probability. Now, what is the interpretation of the resulting probability, which is close to 0.33? That probability means that, okay, if the parameter of the proportion of defective material it's 5%, that's the parameter. Then if we collect a sample of 100 products or doors in this case, the probability that the proportion of defective products in that sample is greater than 0.06, that probability is 0.33. That's the interpretation of what we are doing here. Okay, that was for the proportion sampling. So far we have covered X bar. I'm sorry, this is S square. S square or S is the same. And this is P hat, right? Now we're going to start discussing means differences. When we're analyzing two populations and we want to check which one is greater than the other one, or if the performance is the same, then we're going to talk about X bar 1 minus X bar 2.